Having completed the part on marginal models, and for that matter also conditional models, with a few examples in each of those cases, and actually several in the marginal case, we are now in a position to move to the third family, the hierarchical family, or, if you wish to call it that way, the random effects family, where the association will not be introduced by explicitly accounting for earlier measurements, for example. It will not be done by, let's say, by hand, explicitly including correlation parameters, but we will use, again, latent constructs, latent variables, i.e. random effects. Now, I've mentioned it before, many people have heard about it before. It seems natural to assume that we will now go into the generalized linear mixed models. Well, the answer is, here in chapter 22, not yet. We will actually visit first another model, and that is the beta binomial model. Now, why is that? Well, it's an historic model, but it also has connotations and ramifications in a variety of other models that I will mention before moving to, indeed, the centerpiece of this part, the generalized linear mixed model. Well, if I go back to the linear mixed model, and I keep it very simple, and I say Yij is equal to beta 0 plus, for example, beta 1 times a time effect, whatever, plus bi, plus epsilon ij, I can now start to think of places to move the random effect to, but there is really not much place. Everything is nicely linearly related with everything else. If, on the other hand, I have binary data and I say, I look at the probability that Yij is equal to 1, and I write that as e to the power beta 0 plus beta 1 times time divided by 1 plus e to the power beta 0 plus beta 1 times time, and if you wish, plus epsilon ij, it seems intuitive to say we include the random effect into the linear predictor. So it's in the linear predictor scale, which is a continuous scale, and then normality, which is also a whole real line scale, seems an obvious choice. But maybe we can say, well, in a given cluster, the probability of success is random because, well, certain dams, if we think of the NTP data set, may be more successful than others. And that calls for random probabilities. Now, of course, in a model that I've just drawn here, if I make the logit random, everything becomes random. But maybe we can draw from the probabilities directly. And that's what in the classical beta binomial model has been done. It's an old model. It's usually used in a clustered context, and the reason is simple. The model can only be used when you have cluster level but no individual level covariates. So again, to translate that on the NTP data set, there can be dam level covariates like those, but there cannot be individual level covariates like fetus level covariates. That's not possible. Okay, so the way to think about it is, well, my outcome, so think of the cluster mates, they follow a Bernoulli distribution with a certain probability, and I've denoted that probability by bi here, but that probability is random. And given those random probabilities, the litter mates are further independent. In other words, we assume a conditional independence model. Just like with the classical binomial thinking out of Bernoulli models, we can also here just look at the sum of the observations. That's all it takes. So we can now say we draw from a pool of probabilities, from a distribution of probabilities, and what will that be, you guess? Well, probabilities need to lie between 0 and 1. What is the privileged distribution living on the 0-1 interval, or family of distributions? The beta family. So I draw from a beta distribution and I have a probability, and then I conduct a binomial experiment within that cluster. And that's what we call the beta binomial model. So I have a classical binomial distribution of the form pi to the power y, 1 minus pi to the power n minus y, with n the total number of cluster mates, y the number of successful ones, n minus 1 the number of failures. And then this is the corresponding beta distribution with its parameters alpha and beta. B to the power something times 1 minus b to the power something. That's a very similar structure. We actually call it conjugate in probability theory, and that's also in Bayesian terminology an important concept. Okay, we have a hierarchical formulation. The probabilities are beta, and given those, the outcomes are binomial. The combination of the two is beta, binomial. Could have been binomial beta also. And one can derive from there, by integrating, that's not very difficult, that this is the marginal density. The marginal density, or the set of probabilities. So if I have n successes, what is the probability, or n littermates rather, what is the probability of having z successes out of n littermates? Well, that's this bottom expression. A summary of useful relationships is the alpha and the beta, of course, they don't say too much. Maybe to you, not to me. I have no immediate insight in what they mean, but there is good news. I can actually rewrite alpha and beta in terms of rho and pi. Rho, the intra-cluster correlation, intra-class or intra-cluster correlation, pi, the success probability. So if you give pi, then you get alpha and beta, pi and rho I should say, but if you give rho and pi, you can derive, if you give alpha and beta, you can derive rho and pi. Now pi is one thing. You can also consider mu. Mu is the expected number of successes. That's of course directly equivalent to the probabilities, right? Because n times pi is equal to mu. And you see that alpha and beta play a role in both. There is also here a connection between mean and correlation this time. And the marginal variance, you can write it down in terms of alpha and pi. It's a good exercise to do that. Take this expression and translate pi and rho into alpha and beta. But looking at it here is actually very insightful. Pi times 1 minus pi times n, that is the binomial variance. But you see that there is a factor here, an inflation or a deflation factor, depending on whether there is positive or negative correlation. If correlation is 0, it just stays the way it is, n times pi times 1 minus pi. But if the correlation is 1, look at that. If the correlation is 1, it would be 1 plus n minus 1, which cancels. So you get, it doesn't cancel, you get the n. You then get, in that case, n squared. And that's a hugely inflated variance. It's the maximally inflated variance. If rho is negative, and how negative can it be? Well, the whole thing needs to be positive. You can work out very easily. The lowest correlation is minus 1 divided by n minus 1. Then there is no variability anymore. Okay, you can rewrite the density, as I said, good exercise, but here is the answer, in terms of pi and rho. And then from here you can actually relatively easily come up with, relatively easily with maximum likelihood estimation. The pi's can be modeled directly, the rho's can be modeled directly with the Logit link and Fisher-Z's link respectively. But in what follows, in some case studies, we will actually look at its use, the use of the model in the context of the NTP data.